Alright, welcome. In this video, I'm going to be recapping CalBC Unit 8. This is our area volume unit. Really, it's our unit where we're going to apply calculus to the things we learned in geometry class. So, I'm going to start by listing out all the topics that we learned about, and then I'm going to kind of go into each one of them and, maybe do a small example problem or something. So, let me just get those all copied down for you real quick. Alright, so on the first day, we learned about how to find the area trapped between two curves. With respect to x and with respect to y, right? If we could write them as either, then we saw that the area of a region was the area of a region regardless of if we integrated in x or in y to find that area. Then we learned about how to find the length of a curve, okay, using calculus, using an integral, and that helped us solve for perimeter problems. Okay? Then after that, we started talking about volumes, okay? And we looked at volumes that were solid, that were rotated, regions rotated around an axis, generating a solid, with no hollowness. That was actually the disks. I think that was what I called A. Either way, it was separated out into three things: the disks, which were solid; the washers, which had some hollowness to them; and cross sections, where the plane region that we were looking at, usually enclosed by a couple of curves, was the base of the solid that we built on top. Okay? And then, on the last day, we looked at free response questions, and what we realized was that, the free response questions that they're asking on the AP exams are exactly the same type of questions we already have a whole bunch of experience answering, throughout these little topics. So let's just go in, and I'm going to write down a couple of regions in the XY plane, and I'm going to keep coming back to these in my examples so that I can show you kind of about all of these things. All right, now for the rest of this video, I'm going to be going back to these couple of regions right here. I'm going to call this region P and that region Q. Okay, so region P is bounded by the graph of y equals e to the x minus 1, y equals 8, and the y-axis, whereas Q is bounded by the graph of y equals e to the x minus 1, y equals x to the 3, and 8. Okay, and I think that this will give me enough to work with to give you at least one example of each of the things that we've done in this unit. Okay, so the first thing I want to talk about is area. Okay, and what I'm going to do, I'm going to just keep reproducing the sketches of P and Q, and they won't be as nice as this one after this, but you're getting the idea of what P and Q mean. Okay, so I'm going to start with area. So 8.1a, and that's area. Okay. We can integrate with respect to x or with respect to y to find area. But, oftentimes the situation is going to dictate which one we're going to integrate with respect to. So I'm going to start with the area of region P. Okay, yeah, that will be something I can do. So that's going to be P right here, and might not always be drawn to scale, but this is y equals 8, and this is y equals e to the x minus 1. Okay, so I'm going to say, okay, if I want to find my area, I'm going to integrate. This one looks like it would be best to integrate with respect to x, and you should always default on that, right? But if you check, you'll see that the top and bottom of this region is always, the top is y equals 8, and the bottom is y equals e to the x minus 1. Okay? So I'm going to say that that distance there is the thing that I'm going to integrate, little tiny rectangles with height given by 8 minus e to the x minus 1. And then we would integrate that with respect to x, as x ran from 0, this is the y-axis, so this would be x equals 0, all the way up to this point. But I don't know what that point is. And so that's going to be something else that we need to be able to do. We need to be able to solve some equations so that we can figure out where these things are happening. So I'm going to start off with, all right, e to the x minus 1 is equal to 8. So that's e to the x is equal to 9. And if I'm solving for x, to get that x out of the exponent, I'm going to take the log of both sides. So that's the integral from 0 to the log of 9 of 8 minus e to the x minus 1 dx. Okay, that one was best with respect to x. Okay, and in this video, I'm not going to be actually computing them all the way because, some of these you need a calculator, and y'all already know how to use a calculator to compute a definite integral, so no. I don't think there's much loss there. Then I'm going to look at the area of region Q. Okay, that was, I don't know, that was a little bad, but it's okay. You get the idea. Equals x to the 3 and y equals e to the x minus 1. If I try to do top minus bottom and integrate with respect to x here, I'd be having, okay, e to the x minus 1 minus x to the third until that corner right there, and then I'd have that 8 minus x to the third. And you could split it up into two separate integrals and you could do it, but if you wanted to do it just in terms of one integral, you need to use right minus left. Right? These would be my rectangles. And their heights would be delta y, meaning that I would have to integrate with respect to y. Okay, so I'm going to need to write these as x as a function of y. Okay? So if y equals x to the third, then x equals the cubed root of y. Okay? And if y equals e to the x minus 1, I could solve for x the same way I did over here by adding 1 and taking the natural log. So x is going to be the natural log of y plus 1. Okay, you can even see that over here in the algebra I already did. So the natural log of y plus 1. Okay, and the width of this rectangle here is going to be the difference in the two x coordinates. So it's going to be on the right, x equals the third root of y, minus on the left, I've got x equals the natural log of y plus 1. Okay, and this is something I'm going to integrate as y runs from, you can see it easiest on this image, from 0 up to 8. So I integrate from 0 to 8 in terms of y. Okay, and then that's how I would get that area in terms of y. Did an area in terms of x, an area in terms of y. Okay. The next thing we learned about was arc length. Okay. So I might be interested in finding, say, the perimeter of region P. So I will say, all right, P. Okay, I feel like my sketches are getting worse and worse, but it's fine. Okay, P. This side length has, this side has length 8 because this is the origin, and that's y equals 8. Okay, we determined that this one went from the y-axis to x equals natural log of 9, which means that that's the width of that line segment. And then this is y equals e to the x minus 1. Okay. Now we know that the arc length formula, or the length of the curve, is equal to the integral from x1 to x2 of the square root of 1 plus dy dx squared. Dx. Okay, so I've got y, I'm going to need dy dx is what I'm saying. So dy dx is going to equal, in this case, e to the x minus 0. So my perimeter that I'm going to be interested in finding is going to be perimeter equals 8 plus log of 9 plus the integral as x runs from 0 to the natural log of 9 of the square root of 1 plus dy dx squared dx. Okay, and that's going to be an expression involving an integral that will give me the perimeter of region P. Okay, volumes. Okay, evidently I said washers came first, but I don't think in any reasonable order would washers come first. I think you start with the discs and then build up. You know, I said I was going to do it first, so I'll do it first. Let's rotate P around the x-axis. Okay, this is region P. We're going to rotate this across the x-axis. Okay, remember that a cross-section of the, after I rotate this around the x-axis, a cross-section of the solid will be a washer. It'll be like a circle, but it'll have a hole in it. So I'm going to need to take two radii. Okay, I'm going to have a large radius and a small radius. So I'm going to start at the axis of rotation, reach to the far edge of the region I'm rotating, and that'll make my large radius, which I generally call A to avoid confusion with the region being frequently called R. And then over here, this will be my small radius. That will be B. Okay, I like to write A and B in terms of X or Y if it's running sideways. But this one, these are vertical cross sections, so it's going to be with respect to x. So A is top minus bottom. Y equals 8 minus the x-axis is y equals 0. And then B is top minus bottom. Y equals e to the x minus 1 minus y equals 0. Okay? And then we know that volume is equal to pi times the integral of the large radius squared minus the small radius squared. Yep, still visible. And this is going to be x still running from 0 to the natural log of 9. Okay? If I'd asked to rotate Q around the y-axis, this would also be a washer scenario. Okay. So I'll do that and this. Okay, that's Q. And I've already done the work to say that this is x equals cubed root of y. If you don't understand where I got this, you need to just rewind and watch me solving for that. And then this is x equals the log of y plus 1. Okay. And so if I'm rotating this around the y-axis, okay, that's the region, or the axis I'm rotating around, I'm still going to have a large radius. Also a small radius. Okay, so my large radius is right minus left is x equals cubed root y, and then the y-axis is x equals 0, so cubed root y minus 0. This small radius is going to be log of y plus 1 on the right and 0 on the left. Okay, so my volume will equal pi times the integral of large radius squared minus the small radius squared. And that'll be as y runs from 0 to 8, the same as it has been the whole time. Okay. Those were a couple of examples of washers. Now we could also have rotated this around like some axis over here, and then right and left would have changed. But overall, my structure of pi times the integral of large radius squared minus small radius squared, that always is going to stay the same. Okay. Now let's move on and look at some cross-section scenarios. Nope, disks. Pardon me. Already forgot about them. Okay, this would be something like rotating the region P around this line y equals 8. Okay, and so this is going to be, okay, this is P, and I'm just going to have one radius, right? If my axis is touching my region entirely, there's no hollowness to it, there's no second radius. So I would just call this my radius. Radius is top minus bottom. Y equals 8 minus y equals e to the x minus 1. You got to be careful with those parentheses, right? And I could call that 9 minus e to the x, making volume equal to pi times the integral of r squared as x runs from 0 to, again, the log of 9. Okay. And that's a good example of disk. Be able to do disks rotating around a vertical axis with Q. I could do it with P, I suppose, but it would look very similar. It would just be right minus left. That would be my radius if I was rotating around this vertical axis, the y-axis, and otherwise it would be pretty similar. Okay, and then the last type of volume we've got is the known cross sections. Okay, let me show you all the formulas you need to know, the area formulas. Okay, this list is by no means comprehensive, but this is like 99% of the AP calculus problems from the College Board, use one of these if they're going to say cross sections perpendicular to whatever axis is square. Okay, well, let's do one square and one semicircle. So I'm going to do Q, cross sections perpendicular to the y-axis are squares. Okay, this is Q. And I'm going to draw the cross-section that's perpendicular to the y-axis. Okay, if there's squares, this is the base of the square. So area equals base squared. We know that volume, now I'm going to need to get this first, and this is cubed root y minus log of y plus 1. Okay, and we know that volume is equal to the integral of area
So that's base squared, so cubed root y minus log of y plus 1. That's my base. I'm going to square it as y runs from 0 to 8. Okay. And then if I wanted to do p, where cross-sections were semicircles, perpendicular to the x-axis, my radius would only be half of that distance. So area of a semicircle, radius is half of top minus bottom. Okay, so my volume is going to be the integral of the area formula, 1/2 pi. Radius is, this is 9 minus e to the x, but divided by 2 because of the half here. 1/2 pi r squared dx as x runs from 0 to the log of 9. Okay, and then, like I said before, when we studied the free response questions, we found that, it was the same exact type of questions that we've been doing all along. So what I'm telling you is, if you need more practice, you need to go back into earlier in the unit and continue practicing. But if you feel good about all this, then you're ready to go. Thanks for watching.